All right, cool. Hey guys, my name is Aiden Glickman.
I'm Cole Howard.
And I'm John Stack.
There we go. And we did a classification MLP model for incremental short selling. So the problem statement is pretty clear. Everybody loves to make money, and a big thing is making money in the stock market. So we decided to try our luck in the stock market. In hopes of exploiting some complex relationships, including some value-based relationships between BYD stock price, which is a Chinese EV manufacturer, and Brent crude oil stock values over a given time period. And hopefully, our model will basically decide whether or not to buy or sell in a given time period following the evaluation. So the data for this, like I said, is BYD and Brent crude oil stock price. And then basically why we decided to do an MLP model is MLPs don't have any temporal dependencies, and the stock market is actually not temporally based. It's at any given moment, any action could lead to an increase or decrease in the stock price, and therefore we wanted to, try some random stuff. So yeah, take it away, John.
Cool. Okay, so I just discussed the baseline architecture and initial baseline results. The model, as discussed, is an MLP. The network architecture we have 4 fully connected layers with RE/LU activation between layers. We have an input layer consisting of 4 nodes, which makes sense given the 4-week look-back window. We have 1 hidden layer with 64 units, a second hidden layer with 32 units, and an output layer of 2 units corresponding to binary classification. The model uses cross-entropy loss and an atom optimizer of a learning rate of 0.001. Training runs for 100 epochs per execution, with batches shuffled to minimize overfitting. Now, if we look at the baseline results, they're pretty good. The black line indicates 0%, and the red line indicates the return of simply buying BYD and holding it until the end of the test period. Average strategy return is 20.43%. Average buy and hold return is 9.89%, so more than double better. Standard deviation, however, is rather high, 22%. So this is essentially a high-risk, high-return strategy of a compellingly high average return. Over to you, Cole.
All right. So now over to how we improved the model. So we implemented what's called a Bayesian optimization on the hyperparameters. And so essentially what a Bayesian optimization does, it's a global optimization algorithm. Essentially, you just want to iteratively train a surrogate model, essentially mapping an input to an output, where the input is whatever your design space is, in this case our hyperparameters, and our output is the variable we're trying to optimize, which would be our average monetary return. And so after we performed this Bayesian optimization, we actually found that using 1 hidden layer was better than the previous 2. And this hidden layer was best with 28 neurons per layer and 100 epochs of training. And so we can see in the final figure on the bottom here that our model's performance significantly increased. So whereas before it got an average return of about 20%, it's getting one closer to about 50% on average now. We also have a roughly the same standard deviation, but the minimum is significantly higher than the minimum compared to the first model, and a significantly higher maximum return as well. And one quick note: both of these models were generated by running 100 cases of our model and plotting a histogram of the results.
And we wanted to really emphasize that, in our pre-work literature review, we didn't find any models using MLPs for financial analysts. And we think this is because RNNs are the typical usage given their temporal aspects. But like we stated previously, we wanted to try a different route, and hopefully it looks like it panned out well. So yeah, thank you for reading or listening.
Thank you.
All right, thank you.